Okay, so modeling evolution is what we have to do in order to understand or to give a representation of what's actually happening on the branches of a phylogenetic tree. So what's a model in general terms? A model is always a simplification of the reality based on current human understanding. We model reality because the reality is too complex to be grasped and to be integrated in a mathematical model, in a model from which we can perform computations. So a model must be simple enough in order to enable us to calculate things pertaining to what is modeled. Okay, so it must be simple enough to be computationally tractable. And the model must be complex enough to lead to measures, findings, or simulations in approximate agreement with our observations. Okay, we observe the reality. Here we observe the biological evidence, and we want to be able to design models that enable us to come to conclusions that are not in complete disagreement with our observations. Okay, if your model fails at predicting, even roughly, even in an approximate way, the reality, then your model is simply useless. So whenever one designs a model, one has in mind to have this trade-off between extra simplicity and extra complexity. Extra simplicity leads to results that are not accurate, that are not conforming with the reality, and extra complexity leads to models that make us impossible to calculate anything. Okay? Models can be used to infer predictions, to predict something about the reality. So the two problems must be that you must be able to calculate your predictions in a reasonable amount of time. That's the tractability issue. And second point is that you want your calculations, your results, your predictions to be in agreement with the reality of the observed facts. There is a quote by Einstein here. It can scarcely be denied that the supreme goal of all theory is to make the irreducible basic elements as simple and as few as possible without having to surrender the adequate representation of a single datum of experience. So the model must be as simple as possible, but it must be able to represent all the data we have, or to account for all the data we have. You can say it in a shorter way: everything should be made as simple as possible, but not simpler. What is a model of evolution specifically? With a model of evolution, we want to describe what's happening on the branches of an evolutionary tree, a phylogenetic tree. Remember that the assumption is that along the branches of the evolutionary tree, evolutionary processes are taking place. These processes lead to mutations in the case of amino acids or nucleotides, and these mutations occur semi-randomly over time, and that's what we want to model. Okay, so in a model of evolution, we deal with aligned sequences. That's one type of model of evolution, the one we're going to see in more detail. Obviously, you can also try and model what's happening in terms of the evolution of a quantitative trait. For instance, if you build a phylogeny concerned with the diameter of the skull of the species that you're studying, then you will have to model the evolution of a quantitative trait. But in these simple models I'm going to show you today, we're going to talk about qualitative traits, so discrete traits, and these traits will be either the 4 nucleotides or the 20 amino acids. In the explanations that follow, I'm going to talk about models of evolutions pertaining to DNA sequences. So we're going to have characters on the leaves and hidden characters in the nodes of the tree that are nucleotides, one of the 4 nucleotides, A, C, G, or T. All evolutionary models are stochastic. They predict probabilities of change. There is no certainty at all that you can get from a phylogenetic tree. Okay? A phylogenetic tree always gives you information in terms of probability for something, probability for a change from one nucleotide to another, probability to have a certain amino acid or nucleotide, featured in one of the internal nodes that correspond to extinct species, etc., etc. It's always in terms of probabilities, okay? And you can also say, okay, we trust this phylogenetic history, we trust this tree with this amount of certainty that is never 100%. So we're going to model evolution in terms of character substitutions. We're going to have this in the slides that follow. Every probability I write PR. I don't know why it was P here on this slide. So we are going to deduct from our model of evolution those kind of things. And this means the probability to have a mutation from A to C over a time t, or over a time t, or for a branch length t, let's say. So that's what we want to be able to calculate. If you have an A at one end of a branch, on one vertex, on one of the 2 vertices connected by a branch of length t, what is the probability that you have C at the other end? These kind of probabilities are going to be derived from our model. A model of evolution has a certain number of parameters, and these parameters either you set them a priori in an absolute way, or you estimate them from some data. Essentially, all models we're going to talk about, all models in use nowadays in evolutionary studies, are Markovian. Markovian property is the property of being memoryless. The fate of a character depends only on its present state, not on its previous history of mutations. So in other terms, the probability pertaining to the evolution of a character from a certain point depends only on what is this character at that point, okay, not on its past. So trajectories of evolution forget about the past, forget about what's happened before, and you can calculate all the probabilities pertaining to the future from the sole information of what's the current state. That's the Markovian property. We're going to talk about it later again and show how it translates in terms of in mathematical terms. Some models are time reversible, some others are not. Time reversibility, time reversible models go together with unrooted trees usually, and they do not imply any specific direction, specific time direction. In other terms, these models or what's going on if you have A and C at the two ends of a single edge, you cannot predict, or the probability of the model is the same whether the time has elapsed from A to C, from one vertex to the other, or from that other to the one. So let's define a few terms that are in use when we talk about models of evolution. The first term is stochasticity. Stochasticity means something that is that contains some form of randomness, and from which you derive probabilities. Okay, so stochastic models are based on stochastic processes, and these processes define the trajectory of some random variables. It's important to consider that for any site in your nucleotide alignment, the character on this site is like a random variable that evolves all along the branches of the tree. Okay, so we are dealing with random variables. I give two examples of models for you to understand the difference between non-stochasticity and stochasticity. For instance, this first model that would say that for some mysterious biological reason, nucleotides mutate once every 1,000 years according to the cycle from A to C, from C to G, from G to T, and from T to A. And that forms the cycle, and we're back to A. Okay? If for some reason evolution would happen as predicted, as stated by this sentence, this model, then evolution would not be stochastic. Okay? In other terms, you can predict with 100% certainty what will be the state of a nucleotide given its present state. What would be its state after, I don't know, 20,000 years, okay? Just apply this model of evolution that is non-probabilistic, that is deterministic. In other way, non-stochastic means deterministic. And then you would know what's the final state without any uncertainty. So obviously, this model is not realistic. Observations have shown that this is not what happens. Another example, this time of a stochastic model, would be this one, the second one. Nucleotide substitutions occur randomly at a constant rate alpha. That is the expected number of substitutions per site per time unit. And that would be, this constant rate alpha would be equal for all substitutions. Now, we don't know if this is the reality of molecular evolution. And in fact, we know the reality is not this one. But nevertheless, this stochastic model approximates a bit better the reality than the non-stochastic model. Okay, the reality is closer, what happens in reality is closer to this than to that. And you see that in this second example, we have one parameter, that is alpha, that has to be estimated or has to be given, has to be found in some way. Okay, this assumption, modeling assumption, is the one that prevails in the model that is called JC69 from Jukes and Cantor 1969. Okay, so this is stochastic because I tell you, because there is this keyword randomly, and you cannot predict, you cannot tell me if I ask you, okay, is a substitution going to happen between time 1000 and time 1100? You cannot tell me yes or no with certainty, because you just have the knowledge that there is there are substitutions occurring, but at a constant rate, but randomly, according to a certain random model, random generation model for substitutions. Okay, next property, very important, and you'll come across this word again and again in different fields of modeling. It's a Markovian property from a mathematician called Markov. It's a very important property, but also very simple to understand. So let's sample points across the timeline, and let's say I have t0, t1, t2. These are 3 points on the timeline. The evolution goes from left to right. And I want to know what's the probability, what are the probabilities for my nucleotide at time t2. Okay, so understand that now if you want to describe the probabilities for a nucleotide at time t2, remember we have an alphabet of 4 nucleotides. So if you want to say what is the stochastic state of your random variable at a certain time, you give an array of 4 probabilities summing up to 1. Okay, you would have probability that it's an A, probability that it's a T at time t2, probability that it's a C or a G. Okay, and these 4 probabilities must sum to 1. We want to do this. And imagine we know what's going on at time. What is the state, the probabilistic state of this specific nucleotide, the specific site, that we're interested in. We know what it is at time t0 and at time t1. So we have an array here of 4 probabilities. We have this array of 4 probabilities, and we want to calculate what is the array of 4 probabilities at time t2. The Markovian property of a model, so if we use, better say this way, if our model of evolution is Markovian, then to calculate the state at time t2, we only need the state at time t1. The knowledge of the state at time t0, when we know also the state of this random variable at time t1, the knowledge of the state at time t0 is useless for us to calculate what's happening at t2. Okay? So this is described here in mathematical terms. It says that the probability for this random variable x describing the state of a nucleotide, this random variable varies over time, x at time t2, the probability of x at time t2, knowing the combination of x at time t0 and x at time t1 is exactly the same that the probability of the state at time t2 knowing the last stage known here. Okay, so it's t1 because t1 comes after t0. If you want to think about the Markovian property concerning the evolution of human beings, the microevolution of human beings during a lifetime, this Markovian property would say that what you're going to be in the future depends on what you are now. Okay? Not on what happened in the past, but on what you are now. Okay? This fully determines what you are now, fully determines what you're going to be in the future. Okay? So we can say this makes sense, we can say maybe it's wrong, but in fact, if you think about it deeply, what you are now encompasses what you've been through. Your whole experiences in life. So it makes sense in a way to say that our life can be Markovian, because if you consider fully what we are today, it's enough to predict maybe our future. And the previous points, the previous time points are in fact included in what is the present time point. Okay? Okay, so basically, if you have knowledge of the state of a character at a certain time, in order to predict what's going to happen in the future, you won't add any useful information if you consider what's been in the past. That's the Markovian property. So the Markovian property is very convenient and and enables us to have tractable models, because it means that the calculations for the future times are based on what's at the current time point, okay, and not on the past. So you can forget what's before that. And you can see that if we were to use non-Markovian models, it would be quite intractable, because you would have to store all the history here on this timeline that is not discrete but rather continuous. You would have to store a potentially infinite amount of information pertaining to the past time points in order to calculate your estimation of what's going to be the state of this nucleotide at a further time point. Okay, so all models of evolution we use nowadays are Markovian models of evolution. So they have this property that to predict what's going on at time t2, you have no additional information considering what was at time t0 than you have if you just consider what's the state at time t1. Okay. Here you could add t0, t minus 1, etc. Many different time points here in this curly brace. They do not give you any additional information when it comes to calculating the probability of what's going to happen in the future. Okay, only the information of what's the present state of the character is necessary. Stationarity is another property of most models of evolution. Stationary models accept limits for the frequencies of the characters after the stochastic model has run for an infinite amount of time. So a model is stationary if it accepts a horizon distribution. Imagine that you have you have your timeline of evolution, and there is no speciation even. So imagine a very long branch in a tree. You start with a certain distribution of probabilities for your 4 nucleotides on a certain vertex, and then you let the evolutionary model evolve. Okay. You must understand that the evolutionary models that we're going to use give us, along this long branch at any point, give us this vector of 4 probabilities. Okay, you started with maybe a C at the beginning of your branch, and then you let this C evolve, and you want to know at a certain point, very far after this initial C on your long branch, you want to know what are the probabilities for the 4 nucleotides. Okay. If your model is stationary, it means that this probability, after an infinite length of time has elapsed, this probability is the same. This vector of 4 probabilities do not depend on what was the original nucleotide at the beginning of your long branch. So it says that the probability that from an A you get a C when after a time t that is infinite, okay? So you have, in this example, you have an A at the beginning, what is the probability at the very end, or not at the very end, but at the horizon, the infinite horizon, to have a C. This probability is a constant that depends on the model. We call pi underscore C, this constant, pi subscript C, sorry. This does not depend on A. Okay, so I should have written also another property, for instance here, limit when t tends to plus infinity of the probability to have from t to c after a time close to infinity is also pi subscript c. Okay, so let's have a break here.